Okay. So yes. Yes, sure. There is no problem with that. I will, even while going on, I will say the definitions and such, and either way, yeah, you can also watch them later on and also. So we have this topic we were looking at complex differentiation. Okay. Now, obviously, we have mentioned the motivation and such for this earlier, so I'm going to find that. But I'll just quickly define what complex differentiation, what do we mean by complex differentiation, okay? So here we are looking at a function. We're looking at functions which are from complex plane to the complex plane, okay? So we're looking at functions which are from C to C and simply C to C, and then you fix, well, to be very precise, sometimes we don't want it from C to C. Sometimes it's enough to just take it from a subset of C to C. Okay, usually we take some special kinds of subsets, but for the time being, let's just take C to C. And then you fix a point. We fix a point. Just give me one moment. Yeah, we fix a point, let's say Z naught. Okay, then we say that F is differentiable at Z naught if the following limit exists. Okay, the following limit, I mean limit h tends to 0, f of z naught plus h minus of z naught divided by h. Okay. Now, the catch, the real point to focus on here is that h goes to 0. What does this mean? Okay, this means that this basically means that h, so h going to 0 means that the modulus of h goes to 0. Okay, so h is not a real number here. Okay, h is not a real number. H could be approaching, rather I should just say, it could be approaching the origin, but from any direction. Okay, so this limit must exist for, this limit must exist no matter how you approach 0. Okay, so what that says is that it's a really strong condition. Okay, because you have to check for all possible h and all possible ways in which it can approach. And yes, basically you take any neighborhood around this and all h inside that, for that something must happen. Then you decrease the neighborhood and then you decrease it further, and you see where this quantity, so this quantity, you can call this quantity g of h, where this quantity goes to, if it goes anywhere and so on. And if it does, then we say that f is differentiable, and we give a symbol, and that is obviously just what we use for reals also, just an extension. We just, the symbol, just the symbol for this thing is f dash z naught. Now, differentiability is a really strong condition. So for example, we have seen this, that this function f, this function z going to z bar is not differentiable. Okay, not differentiable in this definition. Okay, but we had seen that it is differentiable if you look at it from a function from R2 to R2 in that weaker sense. So in the weaker sense, it's differentiable, but in this sense, in the complex sense, it's not differentiable. Okay. Yeah, 1 minute. Having some coughing. Yeah, so this is the situation. Now, before going into the theory for today, let me just do a very simple warm-up problem. Okay, it's a very simple problem. It's not even a complex analysis problem or complex differentiation problem. It's just a problem in complex numbers I want to just do before I go more into the theory today. So just call this, I just do this usually, not every class, we don't do this every class, but maybe once in 2 classes, 3 classes, we just do a warm-up problem. Okay, just to, you know, get our this get flowing with complex numbers also, because that's part of the reason we use in the reasoning. Okay, So we basically, the task is to basically find, and it is very simple, but we'll do it. Find all possible values of I to the power I. let's just quickly get this done then. Because being able to reason about complex numbers and such will be essential for us. It will give us clues, symbolic reasoning improves the computations. So we should just be fresh with them. Yes. How should we get started with this? Let's think about that. Yeah, I'm sure all of you would have done this at some point, maybe in high school also. Some of you may have, who are in high school done it. So yes, come on, someone can give some ideas as to how to start. Yes. Okay. So let's wait. Let's try this. And then the real goal of today would be to find a simple sufficient condition, to be able to conclude complex differentiability. Whether something is complex differentiable or not, to check it by bare hand, to check it by limit properties is difficult. So we want some conditions in terms of real differentiability, which will allow us to conclude. That will be the goal for today. And then we'll look at some examples and counter examples to see how strong that condition is and so on. Okay, so you're saying it's a real number. Yeah, that's true. It's not one number, it has several values. Okay. That's one of the values. This is one of the values. Think about hmm, that's right. Hmm. That is right. That's right. Yeah. Sorry. That's right. Okay. But will this give us all the values? So we need all the values. This will just give us, yeah, this will give us one of the values maybe if we simplify this and so on. Yeah, the reason why we are doing this question is because later on we will look into the actual definition of these things, the actual complex logarithm and these things. That's why we are just doing it right now, not conceptually, but just computationally. Yeah, so I think if you guys just try, you guys will get it. So basically, yes, it's basically what it is, but this is not in a good form. 2n pi plus, I think, yeah, it will be, the minus will be outside, something like that. Yeah, and this is now I'll leave it to you people to complete this. This is these are all the values. Hmm? Plus 2 and pi. Yes, yes, that's right. So you have to also put the 2 and pi, and then you put the I, and then you get it. That's right. That's okay. Okay. So this was just simple enough. From That's right. Yeah. But we still do not know what is the actual definition of this. What does it mean to raise something to complex power? You see that that's really a matter of definitions which one has to get into and so on. So, but we'll see them later. First, let us develop a bit more, get a hang of complex functions and so on. Anyways, let's move forward. Now, this is a problem. So it's like an exercise in complex differentiability. So this is very relevant for us, and this will be a very important example. The theme here is okay. The theme here is complex differentiability at a point. Okay, so till now we have defined complex differentiability at a point, and later on we will see that complex differentiability implies much more. It is expected because it's a very strong property, right? It usually implies much more, but complex differentiability only at a point will not imply much. Okay, we will see the reasons. So right now we're just doing an example problem where we will see this phenomena of complex differentiability only at a point. In the real, for a function from R to R, you can probably construct a function which is differentiable only at a point. You can think about how to do that. Okay, but this, let us do this. I mean, so that is probably an exercise which we'll not do now because that's in simple. So function, we need a function from R to R, differentiable only at only at a point and nowhere else. So n is defined on all R, of course, I've written R to R. Okay, that's simple enough. You guys can think about it. But let us do a problem here. Let us look at this function, which is from, well, I can say it's from C to C, but it's in fact C to R, but then that's also in C, so it's from C to C. And the function is, this is important, Z going to mod Z square. Okay. First question is here is, I mean, these questions these are, as I said, we will use these in counterexamples and such. So yeah, is F differentiable at Z equal to 0? Let's first try to answer this question. Then we will move forward to other points. This will get the hands-on, experience on computing complex differential derivatives and so on. Is F differentiable at 0? And whenever I say differentiable, obviously I mean complex differentiable. So I'm removing this. Sorry. So we'll just use the definitions. We will not use any Cauchy Riemann equation and so on, obviously. Till now, we have not yet proved the sufficiency, so on. Let's just calculate it together, right? It's very simple in sense that we have to just do it, just write the definitions, right? So what if it was, then what would it be? This, what we would write it to be, well, we should not write it right now, but just writing it, h going to 0, it's very simple, right? Just f of 0 plus h, which is just mod h square minus what? 0, right? Just f of 0. divided by h. And we need to take this limit of this. So does this limit exist? Should exist, right? What should be its value? Let's think about that. Absolutely. Can we give more reasoning? Can we give, see, because h is complex. No, this is a complex limit. That will not be enough. That is the whole point. Yeah, you have to take from the entire, all h that go to 0. Let's work this out very, very slowly, or means very in a very detailed way, in the sense that let's write out everything. Soon you will see that these things are, I mean, this is like a, it is 0, it's correct. Okay, but let's work it out, expand it and work it out as if we don't know. So let's write h as h1 plus I h2. And then what does the numerator become? It becomes this. And what is the denominator? Denominator is this. And so then you see, you just work it out. H going to 0, just rationalize and so on. You get h1 minus I h2. You see, just rationalize it and you see. So in either way you will get, and then h going to 0 means h1 and h2 both going to 0. So is that right? Any doubts, please interrupt me, because yeah. Okay. Now obviously it's also very clear, because obviously the numerator is moving much faster to 0, no matter how you go about it. So it's simple. So yes, the answer is yes, and the derivative is 0. Okay. So let me just do one thing, some space. Now let's also, you guys, start thinking about what happens at other points. What happens at other points? Does f dash z not exist? No, but you will, but this will not be the what it is. This will not be there if the point is not 0. Rishabh, is it clear for you so far? Is it, yes, that's why we're just working out it in detail. Yeah, okay, cool. Also, you just interrupt me if there is a question. Let's try out. So let's try out f dash 1, isn't it? Let's just try out f dash 1 and see. So what will be f dash 1? If I write the definition. No, why h tends to 1? So this is just the definition of the derivative. Yeah, h tends to 0. Let's write it, f of 1 plus h minus f of 1 by h. Now let's expand it. This is the thing. So 1 plus h, you just take the mod and square, minus f of 1 is just 1 because mod of 1 is 1. Okay, so I have to write the limit there, but limit Now let us expand this. It's simple enough. So 1 plus just, yeah, just the definitions. That's right. Yeah. Minus 1 by h. So we're just breaking it down to, now let us see. If you keep doing this, just do the calculations. And what do you get? Let's think about it. So we need to know if the limit of this thing is, does the limit exist or not? That is the question. Now think about this more carefully. Let us also quickly define what this means. So once again, I mean, we just want to show that no matter how you approach zero, this quantity must exist. This limit must exist. No matter how you approach zero. So if you approach along h1 very fast and along h2 very slowly, and so on, in every way you approach it, it should go to zero. Okay, right? Because see, the very definition is that if you claim, for example, if you claim the limit of this is L, okay, then what do we want? We want that given an epsilon greater than zero, this quantity should become epsilon close to L for all h less than some delta. So given a degree of approximation epsilon is obviously a real number, right? So that's the degree of closeness. I must be able to attain that by some delta. Okay, so for all h less than some delta, it should work. Okay, it basically means no matter how you approach zero, your quantity should go closer and closer to L. So yeah, how do we prove such a thing? One way is to again just rationalize it and so on. If you rationalize it, things will become ultra clear. Okay. So let's do it. Let's just rationalize it and do, even though there are better ways, but for the time being, let's just do that. Plus 2. Yeah, yeah. In either way, you will get this. No, you will get h1 minus. The point is that in this way, you cannot go wrong. You will just be able to, it'll take some time, but you can do it. Yeah, no, we can also, I'll just separate it because see, limit existing means that the real part should also go to a real part limit should exist in the imaginary part. So it's very simple in a sense that it just have to separate the real and imaginary and just calculate the limits for both. Even though that's not a conceptual way, but it's a short way to do things. And I think it's good to get hands-on experience until we get more intuition behind these things. So let's just do it like this. So we must have, so now we're just down to the real case. This limit should exist when h goes to 0. So I'll just write it. And meanwhile, if someone can think of a better explanation, that's much better. But otherwise, we'll just do this. This should be minus. I mean, again, we have h2, h1 square, h2 square, 2h1. So what about this? That's right. That's right. So something like this, right? So this is just big calculations. And then we have 2 H1, H2. This time it is H1, H2, right? And yeah. So I'll just cut some corners. I'll just say that we can forget about this H1 here because that's obviously going to 0 and also it's also going to 0. Now the question really is just look at one of the limits and see if it exists. Which one? Is it 1? Why do you think it's 1? No, H1 is not equal to H2. That is the point. H1 could approach to 0 much faster than H2 approaches 0. That is the thing. Yeah. So let's think about that. So we have to basically see, will this basically think about like this. Can you make this tend to different places by taking different rates going to this, and then it is, let's just not focus. Let's just focus on the first part and see. Does this, now this is a simple plain question in limits in two variables. Does this limit exist? So here I may replace the h by h1. I'll say h1 comma h2. Should this limit exist? The numerator is only h1 and the denominator is h1 and h2 both. Can you make it approach to different places is the question. Then you can show it does not exist. Or if you want to show it exists, then guess a limit and just do the epsilon delta, just take the difference from it and try to see. These are some good ways, straightforward ways, right? The claim is this limit will clearly never exist. I think so. Yes, that's what I'm feeling, that this will not exist. Because the denominator is like the distance of a point from the origin, right? And that distance could keep increasing, but h1 or, okay, no, I'm sorry, forget about that because it's going to 0. So it can't keep increasing. But still you can take different rates. And this is just a normal trick. I mean, the idea is that if you take different rates, one is that when both tend to 0 at the same, both h1 and h2 tend to 0 at the same rate, which means you are tending to 0 along the line y equal to x, sort of just going in a usual way. So when you tend like this, when h1 is equal to h2, when h1 is equal to h2, then what happens? What does it become? So this is one way to go to 0 when both are equal, and then we have a value, right? What is that value? It's half. This will be half. Half into 2, so it's 1. Is it clear to everyone? Right. So we can, yeah, we just try out all ways to go to 0, and then we have, and this is encoded in the definition, right? Because for all h less than delta, it must go to a fixed number L. But if you can show that it goes to two different things, then obviously that's flawed. Then it cannot have a limit, because then inside that same delta, it's going to two different. It's going to 1, and then what is another way in which you can make it tend to something else? You can clearly make this tend to 0. Yeah, not just greater. Okay, I was going to say less, not because see, if h2, I mean, if h1 is very less than h2, or if h1 tends to 0 very faster than h2 tends, then this will go to 0, right? And just the way to do it is that you put h2 equal to h1 square, just like a parabola. So you come down, but But the y coordinate is going faster. Is going no. I mean the x coordinate is going down faster. The y coordinate, yeah. If h2 is less than h1, you said? No. That is what we already did, and we got the half, right? When h1 is equal to h2. But the other way is you just do this thing, and then clearly this goes to 0 because this is this, and this is h1's. Oh wait, I'm making a mistake. No, it will not go to 0. But in any case, let's just check it out. This is h1 to the power 4. What does it go to? Yeah, okay, so it goes to 1. Oh, so what I was saying was conceptually, so 2 times this. So it goes to 2, which is different from 1. So either way, we are successful. But I was, yeah, it goes to 2. So it's different. It's going to 2 different places if you tend along 2 different ways. But then what I was thinking about, okay, no. So what I meant, then what I should have done to make this go to 0, you can also make this go to 0 if you make h2 very bigger than it. So you have to put h1 equal to h2 square. That way you'll make it go to 0. But in any case, all these are already giving 2 different points. Okay, so this limit does not exist. Okay, this limit does not exist because if the limit was L, okay, then inside some delta, it would be, it will be very close to that particular L, but then it's going to 1 and 2. That's not possible, right? And yeah, and obviously these two things can go to 0. Via these two roots, we can go to 0, and we are going to different places, so it can't go to any particular L. Okay. See, usually the idea is that the numerator is independent of the denominator. Okay, so obviously you can just sort of like, yeah, and you can do something and you can see that it's sort of independent. I mean, you can write it as a ratio, and then you can blow up that ratio. You can see it in many ways. You can just blow this ratio up or make it 0. You'll get different things. In any case, it doesn't exist. So you see this very nice function. I mean, at least from the real perspective, it's very nice. The function that just returns you the square of the distance. That is not differentiable. That's not a differentiable function at any point other than 0. Okay. So the conclusion is that f of z equal to z square is not complex differentiable. Is not complex differentiable. And these calculations are actually very important, just to be able to do this calculation at any point, okay, other than 0. Okay. Why we are seeing this? Because we will soon see that being complex differentiable only at a point is pretty useless from the perspective of the theory. Okay. So it is. We'll see the reasons for that, and meanwhile we can make a definition. Definition is a holomorphic function. Okay. Now, holomorphic function is not actually the same as complex differentiable. It's not exactly the same. Okay. Holomorphic means that I just make a loose definition. Okay. Holomorphic means complex differentiable in a neighborhood. Okay. So more precise, holomorphic at a point z0. Maybe this definition should come later when we actually are able to appreciate the how different those functions which are holomorphic is from those which is just differentiable at a point. But holomorphic roughly means that differentiable in a neighborhood of that point. Holomorphic at z0 means that complex differentiable in a neighborhood of a point. So this is pretty strong, and it's very, very different. Okay, we'll see the reasons later on. First, we'll see what difference it creates, and then probably we'll see the reasons. Okay, so far so good. Now let us just quickly come back to complex differentiation and just look at a few consequences. Then they will basically form our necessary conditions. Okay, so consequences of complex differentiability. So till now I'm just keeping it at a point. Okay, but we'll soon see that this is pretty useless. We get the results, but then we can't get the geometric results. We might get some results at a point, but not really geometric useful. Okay. Last time we did see this, we actually saw this the last time from the perspective of matrices and so on. Okay, but today we'll just see it from a slightly different angle. And the goal is to get sufficient, as I said, to get easy to check, intuitively sensible, sufficient conditions for a function to be complex differentiable at a point and in a neighborhood also later. So what are the consequences? Let's just write the definition. So this means that f dash z naught is equal to limit h tends to 0 by h. That's what this means. But then we have already, so consequences means that we will assume that this limit exists, right? That's how we'll get the consequences, because unless we get some consequences and some, hence that's what necessary conditions mean, right? These are necessary because these are the consequences. Unless we get these, we won't have a sense of how to frame or how to get sufficient conditions, right? Unless you have some necessary conditions, it's difficult. So assume this exists. Now, already we have said, and we have used it also in showing non-differentiability in many places, that this means that no matter how you approach h, you should get the same answer. Okay, no matter how you approach h, you should get the same answer. And that's the reason why z going to z conjugate was not differentiable, because when you approach it along the real and the imaginary, you get two different answers. So with that principle in mind, if you want to get some consequences, you just, when you assume this exists, just check this along the real and along the imaginary. Okay, so put h in real, and in this side you just put h imaginary, because these are obviously these are not enough, right? The h for this limit to exist, no matter how you approach it, should exist, right? But we are just saying, okay, fine, there are a lot of ways to approach. We obviously cannot write all of them, right? But these are two core ways, and don't think that this implies that don't think that if approaching along this makes it differentiable and approaching along this makes it differentiable, then it implies that it should be differentiable. No, that also is not true. But at least these are necessary conditions. Is it clear till now? Okay. So then if you put h equal to real, then what do you get? That is a real question, right? So what should we get? So one can make guesses here. It's not difficult, but let's just write it out. Let's write out everything in details. You see, f is a complex function, but you can say this, but then essentially f is made up of two functions from complex to reals, the real part, and because for every input you get a real part and imaginary part, right? This is what all of us know, right? Obviously, we do understand though that u and v are related. In a good function, u and v will be related. That was the intuition we had. In a differentiable function, u and v should be related, right? Okay. Because you see, if it's a natural function from the plane to the plane, which is maybe through some fluid flow and or some sort of rigidity, something that has some local to global push pull, the real and imaginary part will not be independent. So for example, yeah, I mean you can't just take two independent real functions and put it and expect then the new function will never be complex differentiable. Okay. For example, I mean, if you have fz equal to z, this was not differentiable, right? And hence many functions like z plus z bar, this will not be differentiable. Okay, so the whole intuition of complex differentiability is that there's some sort of tension. Okay, there's some sort of tension in the range value. It's trying to capture some sort of physical motion and such. Okay, we'll make these things more precise later on. And in these functions are independent, which have two independent components, and they are not good. They will not be complex differentiable. But we will see these things. So basically, U and V will be related in complex differentiability. That's the intuition. But this will make it precise today, rather just in a different way of what we have already done. In any case, so if we put this, I mean, now at this point, when you put it here, what do you get? Let's just see. So here H is, real. So maybe I should rather be more careful, and I can just say H1 comma 0 going to 0. Okay. And then we have, instead of F, I'll put U. And instead of Z, I will just put X naught comma Z naught. I'll put X naught comma Y naught. So we'll put X naught plus H1, okay, comma Y naught plus H2. But now H2 is 0. We are approaching along a special way. So I'm just putting the values. I'm not doing anything. Okay. So this is what we get. And similarly, we'll take this, and this is very simple. So it's X naught comma Y naught. Okay. And then this is one part, and obviously here you have H1, only H1, okay, not H2 is 0. So we get this. And similarly, you get the I, and just quickly write it. So it's more about just patiently writing things and making sure we understand. And then you can look back and you can just, zoom out and just look at everything that has happened. But this is what it is. So what is this? What is this in a more familiar world? That's right. Yeah. So it just says that if you look at, so it in the most minimal language, it just says that when you look at U as a function only in the first variable, if you forget about the second variable, then it's a differentiable function. That's all it means. But now mathematics, we obviously have put a name to it, and we call it partial derivatives, which means the partial derivative of U with respect to X. This is what it is. This is a partial derivative. Okay. So I'll just write it in the language. Yeah. W at X equal to X naught. That's what this is. And similarly, this one is right. No, not Y, it's also X. At X equal to X naught. Obviously, I must also say Y equal to Y naught, but it doesn't matter because, this is Y is fixed. This is what you get. Now, I'm not doing this side of the calculation. Please work it out. But if you do it, you will get. No, actually, let's do it because there is a thing here. Let's do it here. So if we bring it down here and do it, what do we get? Can anybody also work it out and tell me what is it that you will get? So we have limit 0 comma H2 basically, or maybe if I should use uniform language and just say IH2. But then no, I should use this language. I think that's okay. IH2 is what it is, and that's the same thing. Okay. And so now this time we put U. So we have U X naught, and this time X naught doesn't change. Just changed Y naught, and then Just it's not y naught. And now you put a I. Should have. Yeah, presentation is bad. So we're just doing it. We're just doing these things. It's simple things, but basically we're doing it. And that's what we need to realize, that these are simple. One has to just do it. And then we have y naught plus h2 p y naught. And then we have h2. So again, this time, not h2, but we will have IH2. This is the difference maker, you see. The I will be there because of the very definition, okay? And here also the I will be there. So now what are these things? So will obviously be equal. What are these things? So the first thing, this, if you just take the I out, it is again basically the derivative of u, looking at it as a function of y at x0 and y0, not writing that now. And then here we have, wait, I made a mistake. No, it's fine. And we have v, and again, once again, we are looking at it like this. Is it okay? So you see, we are getting that these two things are equal. So I'll just remove this. No, yeah. So how are we getting this? This is just a consequence of assuming that. So it looks like a very small consequence, given that you must approach from all directions and see what are all many things you can get. But this is certainly what you get. This is certainly something that you get, right? If you just check along the reals and then along the imaginary, they should obviously be equal, because obviously in all possible ways you approach, you should get the same answer. They're equal. So what can we say from here? Wait, have I made any I feel like I made some mistake, right? In the calculation, because the del u, one second, have I made? So the del ux is del vy, but then here, oh no, there was a minus. No, but the minus is fine. Wait, let's just check. I think I made a mistake, because even the matrix, we don't get this. One second. No, the I is in the denominator, right? So when it comes in the numerator, it goes with a minus. So that was a mistake. Yeah, the I was in the denominator. Yeah, okay. So I was thinking, okay. So what do we get? We already have some important necessary conditions, which means that now you can already start proving that a complex function is not differentiable, right? If it doesn't satisfy this, then you can just discard it immediately. And this will usually be enough in the easier questions to say something is not complex differentiable. It's a fantastic result. You see, the derivative of u with respect to x is equal to derivative of the imaginary part with respect to y. A remarkable issue. No, we don't have. Most of the times you don't. So the complex differentiability is a very strong condition, because the definition is made like that, and it tries to capture some very rigid physical phenomena. So it's not about just finding tangents and all that. Okay, it's much more, much different maybe. Is this? So see, one must realize this very clearly, that these are not a priori sufficient conditions. Okay, these are only necessary conditions because we assumed it's differentiable and we got these consequences. Okay, that's the thing. Now we had seen this in a different way. If you don't remember it, please go back and look at it. That way is actually much better. Okay. The other way. So the other way was we had seen this through matrices. Okay. And that actually leads to some very interesting things. So in any case, I'll just quickly mention it. I also want to prove that this is sufficient. In what way? Continuity. That's right. Yeah. No, yeah. No. But this is not sufficient. But it is sufficient in a very. It's almost sufficient. That is the magic in the complex situation. Okay, and that is a little counterintuitive, but it is almost a sufficient condition, and that's what makes it so powerful. Now to show something is complex differentiable, you have to basically just check this. But we have not proved that part. That's hard. That's a little difficult to prove. We will see that next time. But I'll just quickly review the way we had seen this through complex through matrices, because that's really the very nice way to see. So when we were looking at the definition, and this is the alternate definition which will also be useful. Basically, see where we write the limit definition, and one side is f dash z naught, but you can pull everything on one side and tell yourself that look, f dash z naught is just a number. It's just a complex number, right? This. And you can just replace this by some number L or D, whatever, D, complex number, right? If there is some D, if you can find some D which makes it 0, then that's it, because obviously it's unique, right? If you can find some D which makes this work, and these are the alternate ways to see differentiability through approximations, because initially we see through slopes, but then through it's a linear approximation of a function. We'll go in the details of that next time. But these are the ways in which we will use to prove that these two equations are actually sufficient. It just with just a small condition, and very, very natural condition. Okay. In any case, let's come back to the point. We had said that this is what it is, where D should be some complex number. Okay. Now, if you change your perspective, and if you look at it from the perspective of a function from R2 to R2, now this is a slightly advanced perspective. Not advanced, but if you have not done multivariable calculus, then it might be. But just look at the video I had explained it the last class. Okay, because of this out of time. Otherwise, I'll explain it in the next class if someone wants to. I think it will benefit all of us. It's different. But either ways, if you look at it from a function from R2 to R2, then you see this is a function from R2 to R2. This is a function from R2 to R2, right? So what is this? I'll just say that this is. Let's just go in details here. This is just a vector. Yeah, if you look at it like that, then this is just a vector like this. Yes. So this should be h1 and this should be h2, right? So on. And this, and then you take the difference with this vector. So you see the point. Comma, and so on. You just write this definition. Minus, now, if you're looking at it from the perspective of R2 to R2, okay, then H is also a vector, right? If H is a vector, then what should you take D to be? D should be a matrix. D should be a 2 by 2 matrix, right? Because then only you can make sense of the multiplication, and it will be a vector. And you can say, why can't I take D to be just a real number? Obviously, one real number is not a good definition of differentiability in two variables, right? Because we had also discussed that. But in either case, the definition also says that there should be a matrix D. If you look at it from the perspective of the real R2 to R2, there should be a matrix D, right? There should be a matrix D. And let's just say the matrix is general. There should be general matrix D, and which satisfies all those conditions, right? But you see, this matrix D should also do the job of complex multiplication. Okay, this matrix D should do the job of complex multiplication. So if D is a number D1 plus I D2, then D times H should be, if H is H1 plus IS2. Then if you work this out, that D should do the job of this, then this ABCD cannot be a general matrix. We had seen that, right? This has to be A, this has to be A, and this two have to be equal. Only signs have to be opposite. This is what it has to be. Just if you basically just find a matrix that does the job of complex multiplication. Okay, just try it, and also you can just see it and so on. But if you want, I'll explain this R2 next time. But in any case, this is what you get, right? And this is what you see. This already suggests that, and these are the partial derivatives, which I also explained. Okay, but in any case, you can all just see that the partial derivatives will be related. This is what this tells you. Okay, but it actually tells you, but why is this technique better? Because it actually tells you that it actually tells you more. Okay, it tells you that complex differentiation is angle. If a function is complex differentiable, then it's angle preserving. Okay, because now we can replace this by a matrix here. Now this is getting loose. I'm not being rigorous here. You can do this. Yeah. If you guys know, you can check it also. That what this matrix does, if you input a real number, if you input a vector, what this matrix will do, it will rotate it by some fixed angle theta. No matter what vector you input, it will rotate it by the same angle theta, and it will scale it by the same factor. And you guys can guess the factor. It's a square plus b root over a square plus b square. You would recognize this. It's like a rotation matrix. That's what this matrix does. Just try out some inputs and you'll understand. Okay, just take some values, 1 1 minus 1 minus 1 minus 1 1, and you will see it just rotates things by the same fixed thing. So it's a rotation. Now this being differentiable means that f of z naught plus h is roughly equal to f of z naught plus this complex number, this rotation. You can just actually write it as a complex number. I realize no need to say it like that, times h for small h, right? When h is small, then this is roughly what it is. Well, it is more than that. It is equal to some other function which goes to 0 as goes to 0, but this is definitely true. Okay, it's a very good approximation of f of z naught plus h. So around z naught, f is just, the function is just this. What does it mean? It means that around z naught, it takes a value. When it takes h, it just rotates it and scales it, because that's what this does, and just adds back the z naught, right? So it just means that if you have the point z naught, and if you take a slight extra vector h, okay, and you want to know where this goes, let's say the z naught went somewhere here, or let's say it went somewhere here. This is f of z naught. Then where will the h go? The h will get rotated by that same angle theta, roughly, if an h is very small, right? It will get rotated by the same angle theta, and it will get expanded by the same amount, right? And obviously then, so h gets rotated and expanded, and then it comes back here. It comes here, because that's what adding this means, right? So basically, the point is that in a small neighborhood, the input values all get these values sort of all get rotated. So there is, as if there is some sort of a rotational force, right, which is rotating and expanding, like a swirling going out. That's what complex differentiation does to the plane. That's what a function which is complex differentiable does to the plane. Okay, it rotates the points and it pushes them a little forward, but the amount of rotation is the same. If you fix a point and keep a very small neighborhood, then that amount of rotation is roughly the same. Okay, this has huge consequences. We'll see. Okay, so we will try to understand the consequences of this thing. Actually, let's say that right now only. Basically, one of the consequences of this is the following, and this, for those who have done Olympiad geometry, inversion, and so on, we'll probably discuss a bit of that next time from this perspective. But what this means is that, let's say you have a curve like this, and then you have another curve like this. Okay, now there is some angle between the curves, right? That's defined by the angle between the tangents. If you apply the complex function f, then obviously the curves can change, right? This curve may become some very different curve. That red curve and the blue curve may become, just saying, okay, the blue curve may become something different. But this angle, now you guys know what I'm mean by this. I mean the angle between the tangents. that will not change. That's the magic. And that's not so surprising now. Okay, think about it, why this is true. This angle, my diagram suggests it has changed, but the angle has not changed. So there's a rigidity. That's why the angle is not changing. There's a rigidity, right? Because it's like if this is pushed a little up, then this must be pushed a little down. There's a rigidity. That angle between curves does not change. These are called conformal mappings. Okay, and one can actually prove it rigorously, but we have already basically proved it. Okay. I mean, what are we trying to say? I mean, if you fix this point z0, and if you look at this point f of z0 plus h, you can look at this tangent. 1 second. You look at this tangent, and you can look at this tangent, and then you get a certain angle, right? Now you see, we know that. So this is theta, and then we were trying to understand what this is. Okay, now if this is theta 1, so if this angle is theta 1, then we will show that this theta 1 and theta are roughly the same. So if you basically, I'm trying to say that you can make the difference as small as you want. Okay. So how do we prove it? Yes. So my point is that if you take a small neighborhood, take a very small neighborhood, right? Then this vector along the first tangent along T1 will get, in the image, it will get rotated by the argument of this angle, and it will get stressed by the argument of this vector, and it will get stressed by this magnitude of this vector, right? So T1 will go here, and it would have been rotated. That's all that matters. The stretching doesn't matter here, right? It will get rotated by a certain angle. This T2 will also get rotated by the same angle. There will be an error epsilon, but you can make that error as small as you want. That's what this means, right? That is, you can make this difference as small as you want, right? So roughly speaking, you see, that's what's coming out to be, right? That the angle, so both get rotated by the same angle. The angle between the curves does not change. Okay, I'll do a rigorous proof of this next time. Before that, I'll go in the sufficiency of this, because that's important. Okay, then we will move into it. Okay. So I think I'll stop here today. Okay, so usually I'll start at 8:45 maybe, so I can take my time. Yeah, I think I'll just stop here today. Not so well also. Yeah. Okay, so are there any questions? Yeah, please, you can just ask. Want me to go back at something that I said? Or okay, and you guys can just take some good complex functions and just check that this is indeed true. Take some complex function, break the real and the imaginary parts, take the derivative, and check that this is indeed true. Okay, so that is something that you can try to. Okay, then. So if there are no questions, then that's it for today. Thank you. Do I have to say no? Nothing else.